This video will be a brief, I hope brief, review of the important chapter information for the test. I sincerely think that you'll find the test to be less horrific than you might be expecting. All right, let's dive into it here. Some things you have to be able to do. Conversions. There'll be several questions where you'll be given perhaps a degree measure to convert to radians, or a radian measure to convert to degrees. The trick is, and there's not much to remember except that, you either are going to multiply by pi over 180, or you're going to multiply by 180 over pi. So the question simply comes down to which of those two do you use, and it's self-evident. If you're going to switch to radians, you know that your answer is going to have a pi involved. Therefore, you want to multiply by the one that's going to give you a pi in the numerator. Well, that one certainly won't, but this one will. There you have it. So for this guy, it's going to be get some ink. It's going to be 120 times pi over 180, reducing 12/18. That's going to be what? Divided by as 2/3. It'll be 2/3 pi. And that certainly looks like radians. If you were to multiply by the wrong one, what would you have had? If you multiplied by 180 over pi, you'd have 120 times 180 over pi, and you would get a totally ridiculous answer of some huge number over pi. And when have we ever seen anything like that? No, you know that's not right. To go from radians to degrees, well, which one? Again, makes sense. You want the pi to disappear. We want to end up with degrees. So you want the pi to disappear. How do you make the pi disappear? You certainly don't multiply by that one. If we multiplied by that one, we'd have a pi squared in the numerator. Whoa, jump back jack. Now, we want to multiply by 180 over pi. So we have 3 pi over 4 times 180 over pi. The pi's cancel, as we hope they would. 180 divided by 4 is what, 45? So we have 45 times 3, which is, I believe, 135. You're done. That answer seems reasonable. So the conversions, you only have to remember to do that or that. And which one do you choose? You choose the one that works. You choose the one that gives you a sensible answer. You choose the one that either puts a pi in the numerator or eliminates the pi. So that should be free points for everybody. All right, the language here. The test I'm going to give you will be another one of these tests that is going to be generated by the computer. And some of the language is language we haven't seen much of, such as, given a point on the terminal side of an angle theta, find whatever. Given a point on the terminal side of an angle, what's that mean? We go back to the idea of not necessarily a unit circle, but a circle. We have a point such as -4, 2, -4, 2, the point -4, 2. That is on the terminal side of an angle. Remember what the terminal side is? Terminal side of the angle. So we're just talking about this angle here, and we're talking about that triangle. Well, if that's the point negative, and this, by the way, is not a unit circle. Don't let that confuse you. This is not a unit circle. Circle, yes. Unit circle, no. What's a unit circle? A unit circle has a radius of 1. Well, if that's -4 and that's 2, this can't be 1. But we need to find out what it actually is. Well, -4 and 2, we know the lengths of those sides and the direction. So we have to figure out the hypotenuse. Yes, we go back to a squared plus b squared equals c squared, our ancient friend. A squared -4 is 16 plus 2 squared is 4 equals c squared. We have 20 equals c squared, so c is the square root of 20. But let's not leave it that way. Let's simplify radicals. Come on, this is precalculus. It's not pre-algebra anymore. Simplifying the radical, 4 times 5. The 4 goes ching, turns into a 2, square root of 5. So we now know the hypotenuse is 2, square root of 5. From that, finding the rest of the functions is trivial. Well, it's trivial provided you are familiar with our old friend SOHCAHTOA. SOHCAHTOA. All right, we know what we know nothing. Okay, so sine, for instance, sine of theta. I should add in sine of theta is SOHCAHTOA, sine opposite over hypotenuse, opposite over hypotenuse, 2 over 2 square root of 5, 2 over 2 square root of 5. Let's get that error out of there. The 2's cancel. We have 1 over square root of 5, but we have to multiply by square root of 5 over square root of 5. So we get square root of 5 over 5. We're done. Then for cosine, same thing. It's going to be adjacent over hypotenuse. Simplify. For tangent, it's going to be opposite over adjacent. That's just negative 1/2. Then the reciprocals, cotangent will be negative 4 over 2 or negative 2. Secant will be the reciprocal of our cosine answer that we did not just now go through. And sine will be the cosecant will be the reciprocal of sine, or the reciprocal of this guy, which will be 2 square root of 5 over 2, or just plain square root of 5. So I'm rushing through those because that's old, easy stuff. Just use SOHCAHTOA, simplify your fractions, you're done. The tricky part is understanding the wording of the problem, which isn't a big deal. Terminal side of the angle, a coordinate, negative 4, 2. That gives us this side and that side. We figure out the hypotenuse using the Pythagorean theorem. And from there, you've got all your numbers. Plug them into SOHCAHTOA, get whatever function you want. Get them all if you want to. Finding the secant of negative pi over 4. All right, I would suggest drawing yourself a unit circle. Find negative pi over 4. A negative angle means we go that direction. If this is 0, shall we count in the negative direction here? If that's 0, then this would be negative pi. This would be negative pi over 2. 0, negative 1/2 pi, negative 1 pi, negative 1.5 pi, and negative 2 pi. Okay, we're looking for negative 1/4 pi. Well, that's halfway between 0 and 1/2. So we're talking about an angle sitting right there. Do this. Secant. How do we find secant? Well, secant is the reciprocal of, think about it, picture your functions in order and the brackets that I've made famous that are not in the book. And you realize quickly that secant is the reciprocal of cosine. So cosine, let's see, yes. First of all, we have to recognize what kind of angle is this. It's halfway between 0 and 90. This is 45 degrees. All right, technically it's negative 45 degrees. You are responsible for knowing your 45-45 relationships. It is your job to know those. I'm sorry, I can't know them for you. This goes back to your geometry days. We have reviewed it here extensively. Go back to previous sections. I don't remember where I introduced it or where I reintroduced it. But anyway, in a 45-45, you know if this is 1, assuming a unit circle, if that's 1, then this will be square root of 2 over 2, and likewise square root of 2 over 2, because it's going to be isosceles. Knowing that, square root of 2 over 2, and negative square root of 2 over 2, and 1. Knowing that, we can figure out the secant by getting the cosine and flipping it. Cosine, SOHCAHTOA says cosine is adjacent over hypotenuse. That's going to be square root of 2 over 2 over 1. So cosine of theta must be adjacent over hypotenuse, square root of 2 over 2 over 1. But we want secant, we want 2 over square root of 2. And of course, you know the story on that. You can't leave that square root of 2 down there. So we have 2 square root of 2 over 2. The 2's cancel. our final result, square root of 2. So what's the procedure? Locate the angle on the unit circle. Recognize what kind of angle we have here and know your ratios for a 45-45. Fill them in. Recognize that secant is the reciprocal of cosine. Use SOHCAHTOA to get cosine. And flip your answer. Simplify if necessary, and you're done. As soon as you see the word y-intercept, you know we're talking about a graph. Only a graph has a y-intercept. Okay, so we need to perhaps sketch or at least visualize the graph. The graph of what? In this example, the graph of cosine x. Again, another thing that it is simply your responsibility to know by the time of the test. What does cosine look like? Cosine, unlike sine, cosine does not start at 0, 0. Cosine starts at 1, at 0, 1. And it has a period of 2 pi. So from 0 to 2 pi, we have to complete one entire cycle. So we're going if we have a maximum here, we've got to end up back at the same place here. There must be a minimum halfway between the two maximum points. There must be a minimum down here. And halfway between the maximum and minimum, it must pass through the axis here. And halfway between that maximum and that minimum, it must pass through an axis there. And so it looks something like this. And of course, it repeats that forever. So what is the y-intercept? 1. Now, I could argue that you should have known that immediately. As soon as you see cosine of x, you know that one of the foundation, the starting point for cosine of x. Oh yes, it starts here, not there. Oh, well that's your y-intercept. So this should be about a 10-second problem. Now what about the y-intercept of tangent of x? Well, tangent has a different period, you'll remember. The period of tangent is not 2 pi. The period of tangent is 1 pi. So if we have, say, 1 pi here, and we'll put negative, still can't write, negative pi. I'm trying to think and talk at the same time here. All right, if tangent has a period of just 1 pi, we know that tangent passes through 0, 0. We know it has this general shape like that, and if you don't know that, well again, you just have to know it for the test. Stare at the graph of tangent and say to yourself over and over and over again, this is what tangent looks like. This is tangent. Tangent. Memorize it. There's tangent goes through 0, 0. And by the way, that already gives you the answer to the question. What's the y-intercept? Oh, 0. How would we do a better graph though? How would we complete the graph? If it has a period of only 1 pi, it certainly can't do this, because that would be a period of 2 pi. A pi that way and a pi that way, total period of 2 pi. No good. That is not what tangent looks like. Because tangent has a period of 1 pi, it has to go a half pi to one side and a half pi to the other side. It has asymptotes here and here. So it's going to look like this. And by the way, it has to pass to the point 1, a y value of 1 halfway between these, and a y value of negative 1 halfway between these. Where is halfway between, by the way? If that's 0 and that's 1/2 pi, this must be at 1/4 pi. So at 1/4 pi, it passes through 1. At negative 1/4 pi, it passes through negative 1. Those are the hallmarks of tangent. And of course, it repeats this pattern every pi. Every pi. So the y-intercept is 0. It has another y-intercept at 1 pi. And another y-intercept at 2 pi, and 3 pi, and negative 1 pi, and negative 2 pi. It has asymptotes at 1/2 pi, and 3/2 pi, and 5/2 pi. How about inverse cosine of x? Again, why are we graphing these? Why are we thinking about the graphs at all? Because we're looking for a y-intercept, and only a graph has a y-intercept. So, for inverse cosine, well, we know what cosine looks like. And in fact, we do that up here. Cosine starts up here, and then it repeats itself every 2 pi again. So if this is 2 pi, it has to be back where it started. Halfway between, it must have a minimum. And by the way, what is that maximum value? 1. So it does something like this, long story short. But this says inverse cosine. So what do? The whole thing simply gets flipped around. So for inverse cosine, instead of positive 1, we've got negative 1. And instead of positive 1, we have negative 1. And instead of negative 1 here, we have positive 1. So inverse cosine is the same thing, but flipped upside down. And of course, repeats forever. What would happen if I had something like negative 2 cosine of x? Well, instead of a maximum point of 1, you'd have a maximum point of 2. Let's do it in red. And a minimum point of negative 2 down there someplace. And a maximum point of 2. And it would look more like this. It would stretch it to twice as tall as normal. All right, let's go on to some more examples. There is a trick for cosine 51 times secant of 51. No, you don't pull out your calculator. And no, we don't have 51-degree angles memorized. We don't know what the ratios are. We don't know what the sides are. Trigonometry, a calculator could tell us, but we don't want to do it that way. That's too much trouble. Way too much trouble. What's special about cosine and secant? Remember this trick. Lay the functions out in what I call the natural order, which is not the order that Sullivan ever puts them in. He does not show you this simple little diagram. I don't know why. Maybe he never thought of it. Sine, cosine, tangent, cotangent, secant, cosecant. These two in the middle are reciprocals. These two are reciprocals. These two are reciprocals. Very simple. So cosine and secant are indeed reciprocals. What happens when you multiply two reciprocals? You get 1. Done. I could have done sine of negative 38.2 times cosecant of, as long as I use negative 38.2, that would equal 1, because sine and cosecant are indeed reciprocals. You multiply them, you're going to get 1. All right, if we know that the tangent of theta is 3/4, can we find all the other functions? Well, yes, we can. When in doubt, draw your unit circle. We know that this is either in the first quadrant, or all students take chemistry, or the third quadrant. I didn't mention which quadrant we are in. Let's put ourselves in the first quadrant. I should have told you. So, we draw ourselves a triangle. We don't really care where it is. We just know that the tangent is 3/4. Again, you go back to SOHCAHTOA. SOHCAHTOA, T-O-A. Tangent equals opposite over adjacent. Tangent of theta equals opposite over adjacent. Well, if you remember anything about your basic Pythagorean theorem, you'll know that if the legs are 3 and 4, the hypotenuse has to be 5. Or, of course, yes, you could figure that out for yourselves with a squared plus b squared equals c squared, but that's way more trouble than you need to go to, because you should know about the 3-4-5 ratio. Once you know all three sides, you can find all the stuff. Sine, opposite over hypotenuse, that's 3/5. Cosine, adjacent over hypotenuse, that's 4/5. Cotangent is the reciprocal of tangent, that's going to be 4/3. Secant is the reciprocal of cosine, that's going to be 5/4. And cosecant is the reciprocal sine, that's going to be 5/3. Done. Nothing to it. Moving on. There'll be a question or two like this on the test where I'll give you some information about the signs, the SIGNs, the signs of a couple of functions, and ask you what quadrant are we in. You can do that very easily using all students take chemistry. This tells you where the functions are positive. They're all positive in the first quadrant. Only sine is positive in the second quadrant. Only tangent is positive in the third, and only cosine is positive in the fourth. So this tells us the cosine of my mystery angle is positive. That means that my mystery angle must be either here where they're all positive, or here where cosine is positive. Because cosine is negative here and here. But also, tangent must be negative. Well, tangent is certainly not negative there. Tangent is positive there. Tangent is going to be negative here and here. Aha, who gets 2 check marks? The only quadrant that satisfies both of these, where both the cosine is positive and the tangent is negative, we have to be in the fourth quadrant. Remember the numbering system? 1, 2, 3, 4. We're in quadrant 4. Do you recall one of our basic identities? I wish, if this were the regular classroom setting, we would have had a quiz a long time ago on the, I think it's the 7 basic trigonometric identities for trigonometry, all based on a squared plus b squared plus c squared. Actually, they're not all based on that, but we would have had a quiz on that. I would have required you to memorize them. Now all I can do is beg you to memorize them. For instance, sine squared plus cosine squared equals 1. Comes straight from the unit circle and the Pythagorean theorem. We went through this back in one of the earliest sections of chapter 6. The sine squared plus cosine squared equals 1. It comes from a squared plus b squared equaling c squared. And remember, in the unit circle, c is always 1. That's what it comes from. So it's easy to remember. It comes straight from a squared plus b squared equals 1. Sine squared plus cosine squared equals 1. Pretty easy one to remember. Therefore, what's sine squared of 7 pi over 4 plus cosine squared of 7 pi over 4? Folks, if you see this on the test, and you take any time at all to try to figure out the sine of 7 pi over 4 and then square it, you are wasting your time big time. Because it is my hope, it is my expectation that you remember for the test that sine squared of an angle plus cosine squared of that same angle always equals 1. This problem should take approximately 4 seconds for you to realize, oh, 1. It should not take you 10 minutes to try to figure out the values of the functions and square them and add them. What a waste. No. Actually, you should be able to do that in less than 10 minutes, but you get the idea. You shouldn't need to do it. Now, this guy is interesting. Sine, no, he's not interesting. It's more of the same thing. Sine squared of 37 plus cosine squared of 37 is 1. Now, something I do not recall discussing before. It's an observation that we made back in geometry, back in 10th grade or whatever. So you haven't seen it in a while perhaps, and I don't recall addressing it in this chapter. But the sine of an angle happens to be equal to the cosine of its, what's that? Well, think about basic arithmetic here, or basic algebra. 90 minus theta and theta are complements. If this is, for instance, 30, then this would be 90 minus 30, this would be 60. 30 and 60, complements. The sine of an angle is equal to the cosine of its complement. Cool. So for instance, that means that the sine of 30 must actually equal the cosine of 60. If you look up the sine of 30, or you don't have to look it up, you can figure it out from the unit circle. You would have 1/2. Well, guess what the cosine of 60 is? It's 1/2. The sine of an angle is equal to the cosine of its complement. Oh, what's meant by complement? Angles that add up to 90. All right, so what's that do for us in this next example then? Sine squared of 60 plus sine squared of 30. You say, wait a minute, that was supposed to be sine squared of 60 and cosine squared of 60, but it's not. It's, oh, of course. The sine squared of 30 would be the same thing as the cosine squared of 60. Ah, yes, because the sine of an angle is the same as the cosine of its complement. So we really have here sine squared of 60 plus cosine squared of 60, which again is just like these, is equal to 1. All right, back to graphs. Amplitude and period. Okay, you know what sine looks like. Sine does this. By amplitude, we're talking how far up does it go, or how far down does it go. But we're talking absolute value. So whether it looks like this, or whether it's upside down and looks like that, it doesn't matter. The amplitude is still 1. So the amplitude is the coefficient of the whole thing, the number that sits in front of the sine function. If it's negative, make it positive. We take absolute value. What's the period? For sine and cosine, and their reciprocals, for sine and cosine, the period is 2 pi. So to figure out the period from the function, we take 2 pi divided by omega. Omega being the coefficient of x. The coefficient of x. So, for example, for the period of tangent and cotangent, they're different. Tangent's period is not 2 pi, tangent's period is just 1 pi. So you just take 1 pi divided by omega to get the period of tangent. Now, we don't talk about the amplitude of tangent because remember, what is the amplitude of tangent? Tangent looks like this, right? Its amplitude is actually infinite, so we don't talk about tangent's amplitude. That's a non-question. But what does A do? A will change that value. Remember I mentioned when we do the tangent function, it goes through 1/4 pi 1 and negative 1/4 pi negative 1. Well, multiply by A, and that simply changes that 1 into something else. If this were a 4, instead of going through 1/4 1, it would go 1/4 4. It would make it a whole lot steeper. A little bit trickier to graph, perhaps. Let's try to graph these two functions, and I have a window set up for that. But before we go to that window, let's consider two things. Amplitude of this one. Amplitude is 2. Not -2, but 2. Let's put an equal sign. The amplitude is 2. Absolute value of the A number. And the period, which we call T, period is 2 pi divided by omega. What's omega this time? X is not part of the omega. Omega is the coefficient of x. So we're going to take 2 pi divided by 1/2. So I'll multiply by the reciprocal, and you have 4 pi. So this thing has a period of 4 pi and an amplitude of 2. And by the way, because it's -2, instead of going in the usual direction, it'll go in the opposite direction. It'll look like that, with an amplitude of 2 and a period of 4 pi. Let's take a look at what that looks like. Okay, so now remember a little bit of a problem here is that I have a bad scale. Let's just live with it. So, sine. We know what sine looks like. Sine goes through this point. Let's do it in yellow. It goes through this point. It has an amplitude of -2. That means it's going to go down first. Down how far? Down to -2 and up to +2. Its amplitude is 2. To get a good idea of what it looks like, we need to know the period. We already figured out the period. The period is 4 pi. There's 1 pi, 2 pi, 3 pi. Unfortunately, 4 pi is right about there, off the edge. So we have to kind of pretend. So it's going to repeat itself every 4 pi, not every 2 pi. So if it's going to repeat itself every 4 pi, let's see, it has to go through another 0 halfway between 0 and 4 pi. So it has to have another 0 here at 2 pi. It must have a minimum point halfway between these two, which puts that here. But remember, it's -2, not +2, so it's down here. And it has to have a maximum point halfway between 2 pi and 4 pi, which would be at 3 pi, but not at 1, rather at 2, because its amplitude is 2. And, well, that's about all we need to know. From there, what's it going to look like? It's going to look kind of like this. And repeating itself forever, I missed this point, but that's okay, you understand. Why is it extra wide? It's extra wide because omega is 1/2. 1/2 makes it extra wide. We fit only 1/2 of a cycle into the space, the normal space from 0 to 2 pi. We only have half of a complete cycle in that usual space where we would normally find one complete cycle. Of course, they always go in the negative direction as well. All right, let's see if we can clean that up and then do the last example. Y equals cosine of 2x. How much cleaning do I have to do here? Well, that's pretty good. Okay, that was easy. All right. So for y equals cosine of 2x, amplitude is 1. It's right side up because it's positive. So we know it goes through 1, 0, 1, not 0, 0, but cosine starts up here. That's the key difference to remember. Sine starts here, cosine starts there. Okay, omega is 2, so we go 2 pi divided by omega for the period. This one has a period of pi. So we have to fit one entire cycle in the space of 1 pi. So if it started here, it has to end here. If it has a maximum point here and here, there must be a minimum point halfway between. There must be a minimum point down here. Well, it must cross the x-axis halfway between the maximum and the minimum. That would be obviously right there and right there. We do our curve, and there it is. And we continue that pattern. And that's pretty, oops, I kind of got off there a little bit, but you get the idea. So this one is more scrunched this way because omega is 2. We have to fit 2 complete cycles in the space that where we would normally have only 1. Normally we have 1 cycle in 2 pi. This says we're going to have 2 cycles in 2 pi. So we have 1, 2 cycles in the space of 2 pi. And I believe that's all I have. If you understand everything we just went through and can do a little bit of thinking on your own regarding, there has to be some things in there to separate the A's from the A pluses. So there'll be a couple things that require a little bit more thought, but it's all based on what we just saw here today. And that's it. I'm planning again for a Zoom review session on Wednesday at noon for anybody who is interested. And lest I mess everything up by saying the wrong thing, let me just check my schedule. That is correct. Wednesday at noon, watch Google Classroom for your invitation to the Zoom review session. It'll be more of a question answer than a review, because now that we've been through both parts of the review assignment, and we've been through these examples that I got by looking at an old test to get a good feel for what the new test will look like. We've covered pretty much everything. Not much more I can say. But if you have questions, tune in Wednesday at noon. See you then, maybe. Otherwise, the test is Friday. Nothing is due today, nothing is due Wednesday, nothing is due Friday except taking the test. More on that later. I'll probably post on Wednesday detailed instructions regarding the test for Friday. Brace yourselves for A's on this test.